Today, let's look at some operation postulates. These are postulates and theorems, really, that involve the four basic operations: add, subtract, multiply, and divide, but they involve them in a geometric context. First theorem we're going to look at involves segment or angle addition. This is not new. If you recall, when we did Unit 1, we used segment and angle addition. We used them in more like algebra-based problems. But here we're going to present a more formal theorem that allows us for use in geometric proofs. So if a segment is added to two congruent segments, then the sums are congruent. So if we are given that segment AL is congruent to segment EC, we can conclude by segment or angle addition, by segment addition in this case, that AE is congruent to LC. Because if we add segment LE to AL and we add that same segment to EC, the resulting segments will also be congruent. Likewise, we can do the same thing with an angle. If we take an angle and add it to two congruent angles, then the sums must be congruent. So if we know that angle OSF is congruent to angle ASI, we can conclude that with the addition of that middle angle there, that angle angle FSI, we can conclude that OSI is congruent to angle ASF. What if you have a situation like this where you actually have two pairs of congruent segments? Take a look at the diagram on the left that deals with the segments. We have segment DA and segment IE are congruent to each other. And we also have that segment AN is congruent to segment EL. So what conclusion can we make? Well, if we take two congruent segments and add them to another two congruent segments, we can conclude that the overall segments are indeed congruent, so that segment DN is congruent to IL. The formal theorem states that if congruent segments are added to congruent segments, then the sums are congruent. And we have a similar one for angles. So if we have two pairs of congruent angles and we add them together, we will get another two congruent angles. So if congruent angles are added to congruent angles, their sums are also congruent. So far this has been pretty logical. What about for subtraction? Well, since subtraction is really just adding the opposite, subtraction and addition are really the same operation, we can apply subtraction to segments and angles as well. So if we know that segment DE is congruent to segment WR, we can actually conclude that DR and WE are also congruent by subtracting segment RE from them. So if a segment or an angle is subtracted from congruent segments or angles, the differences are congruent. So essentially, if we're using addition, we're going to be going from smaller segments or angles to larger segments or angles. If we're using subtraction, we're going from a large segment or angle to a smaller segment or angle. And again, we have the same theorem for angle subtraction. So if we have the large angle ESA is congruent to EAS, right? We can subtract the smaller angles NSA and NAS and get the other small angle. So if congruent angles or segments are subtracted from congruent angles or segments, then their differences are congruent. So you see we have the single angle addition and kind of like a double angle addition and subtraction, just like we have with segments. Let's look at what this looks like in a proof. We're given that angle HEF is supplementary to angle EHG, and that angle GFE is supplementary to angle FGH. And we know a couple of congruences. We know that angle EHF is congruent to angle FGE, and that GHF is congruent to angle HGE. Okay, so we want to conclude that angle HEF is congruent to angle GFE. Okay, so if we take a look here, just by looking at the diagram, we see we have two pairs of congruent angles, right? So those two pairs of congruent angles can be added together to create another congruent angle. Okay, and then we know some information about the relationship between the angles there on the bottom, that HEF and the GFE, and how they're related to that sum of those angles up top. So we're going to use that information to formulate a proof to prove these two angles equal, or congruent, sorry. Okay, so we start with all of our given information in this case. You can see all of those four pieces of given information listed there in order. Okay, and we can make the direct conclusion, as we talked about in our plan, that angle EHG is congruent to angle FGH, because if congruent angles are added to congruent angles, then the sums are congruent. That was that second instance of the addition property. We can simply call this addition property, but that was that second instance when we were dealing with multiple angles. And then based on that, we can actually directly conclude based on step 5 in conjunction with steps 1 and 2 that angle HEF is congruent to angle GFE because supplements of congruent angles are congruent. Okay, so if we know that HEF is supplementary to EHG, and we know that GFE is supplementary to FGH, we can conclude that those two angles are indeed congruent. We have some similar properties for multiplication and division. If we look at the figure below, we know that B, C, F, and G are trisection points. Well, that's given to us. So trisection points, remember, divide segments or angles into, the points are going to divide the segments into 3 congruent parts. Okay, so if we know that AB and EF have equal measures and those measures are 3, what can we conclude about the overall segment? Well, if those are trisection points, that means that each portion of that segment is 3 units long, so the overall segments are 9 units. So if segment AB and EF are congruent, can we make the conclusion that segment AD and EH are congruent? Well, yes, we can, because again, a trisection means we just divided it in 3. So if a portion of them are congruent, if we multiply by 3, we get the overall measure of the segment, or the overall segment. So by multiplication, we can make the conclusion that those two overall segments are congruent as well. So in the figure below, we're given that KO and PS are bisectors. So if JKM and NPR are congruent, so those overall angles are congruent, what conclusion can we make about JKO and NPS? Well, again, we can conclude that they are congruent because by definition of a bisector, right, we're splitting an angle into 2 congruent angles. But if the whole angle, if both of those overall angles, those larger angles, were congruent to begin with, then each of their pieces must be congruent as well. So let's see how we formally state this in a theorem. For multiplication, if segments or angles are congruent, then their like multiples are congruent. Okay, so if you know that a piece of a bisected or a trisected segment or angle is congruent to another piece of a bisected or trisected segment or angle, then all of the pieces, like the overall pieces all together, must also be congruent by multiplication. And likewise, if segments or angles are congruent, then their like divisions are congruent. Okay, so if we know we have two congruent segments that have been bisected, we can say that those bisected segments, those smaller segments, are also congruent. Okay, so for multiplication, if we're going to use multiplication, we're going from smaller segments or angles to bigger ones. And if we're going to use division, we're going from big to small. And if you're going to be using multiplication or division, you're going to want to look for uses of the word bisect or trisect, or anything that indicates that something has been divided evenly. All right, here's a sample proof. We are told that NOP is congruent to angle RPO. And then we are told that PT bisects RPO and that OS bisects NOP. And further, we're told that angle NSO is complementary to angle 1 and that angle RTP is complementary to angle 3. And our goal is to prove that NSO is congruent to RTP. Okay, so we're going to start with the first three pieces of given information, right? And if we look at those three pieces of given information, we're told that overall angles are congruent, and then we're told that we have some angle bisectors there. So based on that information, we can conclude that angle 1 and angle 3 are congruent by division, right? So if we have overall angles that are congruent and we know that both of those angles have been bisected, then their like divisions are congruent. Or another way of saying that is that halves of congruent angles are congruent. Then we're going to follow with the rest of the given information, that angle NSO is complementary to angle 1 and angle RTP is complementary to angle 3. Those are both given. Okay, and recalling from a previous video, right, the congruent complements theorem, if we know we have a set of congruent angles in angles 1 and 3, and then we know that we have angles that are complementary to those angles, we can conclude that those angles that are complementary are also congruent because complements of congruent angles are congruent.